All right, let's set the scene. It's 5:30 in the morning.
Oh, I know this scene.
Yeah, you know it. The sun's not even up yet. You're out in the yard, breath fogging up in the cold air, coffee in one hand, and you're just staring down a truck refrigeration unit that will not cooperate.
Mm-hmm.
You hit the start switch, you hear it try to turn over, and then silence.
Just that blinking red light.
Exactly. Alarm code 15, check glow plugs.
It is the classic nightmare start to the day for any technician. And I know what happens next in like 90% of these cases.
Oh, I know what happens because I've done it. You drop the coffee, you grab your toolbox, and you immediately start ripping the glow plugs out.
Right.
It says check glow plugs, so you change the glow plugs. Seems like the most logical thing in the world.
It feels logical, sure. It's mechanical intuition.
Yeah.
But in modern transport refrigeration, that kind of intuition can lead you down a very expensive rabbit hole.
Yeah.
If you're just swapping parts because the screen told you to, you aren't fixing the problem.
Mm-hmm.
You're just guessing with expensive components.
And that is exactly why we're doing this deep dive today. We are taking alarm code 15 and we are tearing it apart. We aren't just going to talk about changing plugs.
Oh.
We're going to talk about the invisible stuff, the current flow, the logic board's decision-making process, and, why a fuse isn't just a fuse.
Exactly. This code is a perfect case study for the difference between a parts changer and a true diagnostician. Code 15 isn't just telling you a part is broken, it's telling you that the electrical signature of the entire system is wrong.
Okay, so let's get our hands dirty. We're standing at the unit, we see code 15. Physically, where are we looking?
We're looking right at the engine intake manifold. That's where the glow plugs are seated.
Right.
And just to set the stage, you got to think about the environment there. It is not a clean, sterile lab. It's hot, it vibrates like crazy, and it's subjected to massive temperature swings.
Oh, really harsh neighborhood. And the glow plugs, their job is simple, right? Get hot, heat the air, help the fuel ignite. But for this alarm, we don't really care about the heat. We care about how the electricity gets there. The source material calls this the H circuit.
The H circuit, that is the lifeline. Power has to travel from the battery, through the harness, across the relay, and finally to those plugs. And along that path, there are gatekeepers.
And the first gatekeeper is the fuse. Fuse F5 on the interface board.
Correct. Fuse F5. It's rated for 40 amps. Now, here's where I see junior technicians get confused all the time.
How so?
They look at the schematic, they see 40 amps, and they think, okay, as long as I'm not pulling more than 40 amps, the system is healthy.
That makes sense, though. I mean, if the fuse doesn't blow, the circuit is working, isn't it?
Wrong. And that is a dangerous assumption.
Oh, okay.
Think of the 40 amp fuse like a bouncer at a club who only kicks out people who are starting a literal riot.
Okay.
The fuse is there to prevent a fire. It's there to stop a catastrophic short circuit that would melt the wires. It's a safety device, not a performance monitor.
I like that analogy. So the fuse is the bouncer, but the computer, the interface board, that's smarter.
Much smarter. The computer has a shunt built into the board. Think of the shunt as the club manager with a clipboard, counting exactly how many people are walking in and out. The bouncer, the fuse, doesn't care if only 2 people show up to the party. But the manager, the shunt, knows that if only 2 people show up, the party is a failure.
So the system is monitoring performance, not just, catastrophic failure. And this is where we get into what you call the Goldilocks zone.
Yes, the computer has a very specific window of acceptable current.
And these are the numbers we need to remember.
You need to memorize these numbers. The minimum current the system expects to see is 10 amps. The maximum is 23 amps.
10 to 23, that's the window.
If the current stays inside that window, the computer is happy. The manager with a clipboard marks it as a pass. But as soon as you step outside that window,
below 10 or above 23,
that's when code 15 gets triggered.
Okay, but here's the thing that used to drive me crazy when I was starting out. Sometimes I'd see code 15, but the unit would keep running. Other times I'd see code 15 and the whole thing would just shut down and refuse to start. Why is it so moody?
It isn't moodiness. It's all about context. The severity of the alarm depends entirely on what the machine is trying to do at that moment.
So we have to distinguish between a normal engine start and a pre-trip test.
Exactly.
Okay, let's break that down. Scenario A, normal engine start.
Yeah.
I've got a load of frozen fish in the back. I need to get on the highway. I turn the key.
In this scenario, the controller's priority is the cargo. It wants to run. It knows that frozen fish is valuable.
Right.
So let's say your glow plugs are getting old. The resistance is high and the current draw drops to, I don't know, maybe 8 amps.
So we're below that 10 amp floor.
Right. But the battery voltage is otherwise okay. So the system looks at that 8 amps and says, this isn't ideal, but I can probably still get the engine to fire. So it sets code 15 as a log alarm.
A log alarm. So it just writes it down, hey, check this later, but it lets the engine start.
Precisely. It doesn't want to strand the driver for a minor inefficiency. Now, what if the current goes the other way? Say it spikes to 25 amps.
Okay.
Then it sets a check alarm. It's a yellow alert. It's telling you, we are drawing too much power, fix this soon. But usually it'll keep running unless it hits that big 40 amp safety limit we talked about.
Okay, so that's the logic. When the truck is out on the road, keep the cargo cool no matter what. But the logic changes completely when the truck is back in the yard. When you hit that pre-trip button, the computer stops being a survivor and starts being a perfectionist.
Perfectionist is exactly the right word. When you initiate a pre-trip test, you are asking the machine to self-certify. You are asking, are you 100% ready for the next trip?
And in that context, 8 amps is not good enough.
Not even close. During a pre-trip, if the current is outside that 10 to 23 amp window, code 15 becomes a shutdown alarm.
Boom. Game over.
Yeah.
The test fails, the unit shuts off.
Fails immediately. Because if it can't pass the spec in the safety of the yard, the system assumes it might fail on the road, and it refuses to take that risk.
Now, there's one specific part of that pre-trip logic that I found fascinating. It's this idea of leaking current.
Yes.
Yeah.
This is a very, very clever safety check.
So explain this. The system checks the current when the glow plugs are supposed to be off.
Correct. So the pre-trip runs its cycle. It de-energizes the H circuit. It opens the K2 preheat relay. Physically, there should be 0 electricity flowing to the manifold.
But the computer is still watching.
The manager with the clipboard never stops watching. If the system commands off, but the shunt still detects a current draw of more than 0.5 amps.
Half an amp. That is barely a trickle. Why does the system care about half an amp?
Well, think about what that implies. If you turn the switch off, but power is still flowing, it means you have a mechanical failure in the control system.
Oh.
Usually it means the contacts inside that K2 relay have welded themselves shut.
Wow. So the relay is literally stuck in the on position.
Exactly. And if the system didn't catch that, you would have glow plugs running 24/7. They'd burn out in minutes. Or worse, drain the battery flat.
And then the driver is stranded in the middle of nowhere with a dead unit.
That's the nightmare scenario.
So that tiny 0.5 amp check is actually saving you from a dead battery 3 states away. That is smart.
It is extremely smart. It's a true fail-safe state.
Okay, so we understand the logic. We know the numbers. 10 amps min, 23 max. 0.5 amps leakage. Now let's get to the part where we actually fix it. You're the senior mentor. I'm the junior tech. I've got my wrench in my hand. What do you tell me?
I tell you to put the wrench down.
You were going to say that.
And pick up the laptop. Step 1 is always data gathering. We need to use WinTrack to download the Service Watch data logger.
I feel like a lot of guys skip this because they think it takes too long. They just want to get in there and test wires.
And that is a huge mistake. Because the problem with electrical faults is that they can be intermittent. Maybe the vibration only causes a short when the engine's at high RPM.
You can't replicate that standing still in the yard.
No, but the data logger remembers. It remembers everything. You want to look at the technician user level in WinTrack. It gives you a graph.
Right.
You can scroll back to 4 a.m. when the alarm went off and see exactly what happened. You might see the current spike to 30 amps for 2 seconds and then drop. That tells you something very specific that a multimeter check 5 hours later is going to miss.
That's a great point. It's like looking at a flight recorder. Okay, so we've looked at the data. We have a general idea of what happened. Now we test the system in real time.
Right. Now we move to active testing using the interface board test mode. We don't want to start the engine. We just want to energize the heater circuit by itself.
And we're looking for a specific LED on the board? Yeah.
We are. We're looking for LED 3. When you toggle the test, LED 3 should light up, indicating the board is sending power. And this is the benchmark. You should see a current draw on the display of approximately 14 amps.
14 amps. That is the magic number. It sits right in the middle of our 10 to 23 Goldilocks zone.
Exactly. If you see LED 3 lit and 14 amps on the display, you have a healthy system.
But we aren't here for a healthy system. We're here because we have code 15. So let's run through the troubleshooting scenarios.
Let's do it.
Scenario 1. You run the test. LED 3 lights up, but the current draw is 0. A big fat goose egg.
0 amps means an open circuit. The bridge is out. The electricity simply isn't getting to its destination.
So where do we start looking?
Start with the easy stuff. Check that F5 fuse we talked about. If it's blown, replace it, but, and this is key, ask yourself why it blew. Fuses don't usually blow for no reason.
Good point. If the fuse is okay, what's next?
Check the K2 preheat relay. Is it clicking? Is it actually closing? And then you have to trace the H circuit wiring itself. Look for a break in the wire running to the manifold.
Okay. Scenario 2. You have current, but it's weak. You're getting like 8 amps or 9 amps.
Low current is tricky. It usually implies one of two things. Not enough push or too much pushback.
Not enough push. That means the battery.
Correct. If your battery voltage is low, it can't push the electrons through the coil. But if the battery is fine, you're looking for pushback, which is resistance.
Corrosion, the silent killer.
Exactly. Corrosion on the terminals, a loose ground connection, a dirty splice, anything that restricts the flow.
Got it. Scenario 3, the scary one. High current. You're seeing 25, 30 amps. You're in the red zone.
If you're exceeding 23 amps, you almost certainly have a short to ground.
And this could be inside the glow plug itself?
Yes, a glow plug can fail internally and become a dead short, or, and this is very common, the insulation on the H circuit wire has rubbed through against the engine block.
So the wire touches the metal frame.
And the electricity takes the path of least resistance straight to ground, bypassing the plugs entirely.
And that's what causes the massive spike.
That's the massive spike. That is what blows your fuse eventually. But before that, it triggers the code 15 check alarm.
Okay, now, there is one technical measurement mentioned in the notes that I think we need to highlight because it separates the pros from the rookies. It's about voltage drop.
This is absolutely critical. You cannot just measure voltage at the battery. You have to measure the voltage at the glow plugs while the circuit is energized.
Why does that matter? If the battery says 12 volts, shouldn't the plug have 12 volts?
In a perfect world, yeah. But in the real world, every inch of wire has a tiny bit of resistance. Think of it like water pressure in a hose.
Okay.
If the hose is kinked or clogged, you might have high pressure at the spigot, but barely a trickle coming out the nozzle.
I see. So the battery is the spigot and the glow plug is the nozzle.
Exactly. The spec says you must have at least 11.2 volts at the glow plug.
11.2 volts.
If you have 12.6 at the battery, but only 10 volts at the plug, you're losing 2.6 volts somewhere in the middle. That energy isn't just disappearing, it's turning into heat at a bad connection.
And that heat is probably melting a connector somewhere as we speak.
Precisely. That voltage drop is your smoking gun for high resistance.
Okay, we've covered a lot. We've used WindTrack, checked the LED, measured voltage drop. But there is one final plot twist. The senior mentor always insists on one last step. Trust but verify.
Always. You must verify the current values with an external ammeter.
So this means getting your own clamp meter, putting it on the wire, and seeing what it says versus what the truck's display says.
Correct. Do not rely solely on the display.
But why? The controller is the brain of the operation. Why shouldn't I trust it?
Because the controller is relying on that shunt we talked about to read the current. What happens if the shunt itself is defective?
Oh, I see where this is going.
Picture this. You have a perfectly healthy set of glow plugs drawing exactly 14 amps. But the shunt on the interface board is damaged, so it reports to the computer that the draw is 25 amps.
So the computer thinks there's a short. It throws code 15 and it shuts down the unit. But the glow plugs are actually fine.
Exactly. I have seen technicians replace the glow plugs, then replace the wiring harness, then the battery, and the alarm won't go away. They're chasing a ghost because they're trusting a lying sensor.
That is a nightmare scenario.
It is. But if you put your external clamp meter on that wire and it says 14 amps, while the screen says 25 amps,
then you know the truth. The problem isn't the engine. The problem is the board.
You replace the interface board or the base controller, and the problem is solved. That external verification is the only way to catch that specific failure.
That is a huge save. That one tip alone is probably worth the price of admission for this deep dive.
It saves time, it saves money, and it saves your sanity.
So once we find the issue, maybe it was a bad relay or a corroded wire or even that lying board, and we fix it, does the alarm just go away?
No. Code 15 is a stubborn one, and it must be cleared manually. You have to go into the menu and acknowledge the repair. It won't clear itself just because the condition improved.
Good to know. So don't fix it and then panic when the light is still blinking.
Exactly. Clear the code, run the pre-trip again, and then watch it pass.
All right, let's wrap this up. We've traveled from the cold morning in the yard, through the 8 circuit, all the way to the logic board. What's the one big thing you want listeners to take away?
For me, it's the concept of precision. Alarm code 15 isn't just a dummy light. It is a precise measurement window. It demands that the current stays between 10 and 23 amps. It demands that the wiring is clean enough to deliver 11.2 volts. It forces you to maintain the integrity of the whole electrical system, not just the parts you can see.
That's a great perspective. For me, the big takeaway is the context logic. Knowing the difference between a log alarm and a shutdown alarm. If a driver tells you, the light flashed but it kept running, that tells you it happened during a start. If they say, I tried to pre-trip and it died, you know you're dealing with that stricter limit. That context is your first clue.
Absolutely. Listen to the machine, look at the data, and use your meters.
And stop trusting the display blindly.
Trust, but verify.
Before we sign off, I want to leave everyone with a thought. We talked about that shutdown logic during the pre-trip, specifically that check for 0.5 amps when the system is de-energized.
The leakage check.
Yeah, it really stuck with me. We tend to think of machines as being off when we turn the switch off, but the system is constantly watching. It's sitting there in the dark asking, am I truly off, or is there a dangerous trickle of energy where there shouldn't be?
It's a level of automated vigilance that keeps the truck and the cargo safe, even when we aren't looking.
It's kind of comforting, actually, a machine that knows when to sleep and when to keep one eye open.
Indeed.
That's it for this deep dive. Thanks for listening. Keep your meters calibrated and your connections clean.
Stay safe out there.